The large plastic base part of the LID Boss is almost ready for mold tooling. But how can Eric be sure that the part is rigid enough to support the dynamic action of the shuttle mechanism? Too much stiffness and we're cutting into the profit margin of each unit. Not enough stiffness and we lose accuracy in the lid separator. What would you do to optimize this design? Let's watch Eric take advantage of 3D Experience SOLIDWORKS Premium.
The LID Boss has 4 motors that work together to deliver a single lid to the user. A stepper motor that lifts the shuttle, a servo motor that actuates the lid grabbers, and 2 servos that drive the lid separators. In early prototype testing, he noticed a fair amount of deflection of the shuttle when grabbing a lid, and suspects that this may be exaggerated with his new shelled-out base design. He'll start by setting up a SOLIDWORKS motion study, where he can use inverse kinematics to analyze the physical reaction forces that develop with each cycle. His first task is to simplify the model and create a worst-case scenario by removing all non-structural parts and hardware. He adds physical motors to the motion study and sequences the timing of each event to simulate the complex internal movements. He'll add gravity to the simulation and set up some basic contact between the lids, grabbers, and separators. He runs the analysis and creates a time plot that tracks the reaction moment between the shuttle and the stanchions. Now that he knows the maximum moment, he uses finite element analysis to calculate the maximum deflection of the shuttle and review high-stress regions in the new base design. Eric further simplifies the model to focus on just the shuttle, stanchions, and base. Since the LID Boss has a plane of symmetry, he can cut the model in half, saving on solve time without sacrificing accuracy. After creating a new study, he enters the reaction moment he calculated in the motion analysis, adds fixtures, applies the symmetry boundary condition, and runs the study. Reviewing the factor of safety plot, Eric immediately sees that the stress developed in the base is not a concern, so he moves on to look at the displacement plot. The deformation scale of this plot is visually amplified to help view small deflections clearly. He sees that there's over 2.6 millimeters of deflection at the end of the shuttle. It doesn't sound like much, but with that amount of deflection, the grabbers could miss the lid. Looking at the underside of the base, he sees that flexing at the stanchion mount is the primary cause of the problem. He's going to have to add some rigidity to this base. Eric decides to stiffen the design with some additional ribs. He reruns the analysis. The deflection plot looks way better, but Eric really wanted to stay below a 1 millimeter threshold to be safe. What else could he do to add stiffness to the base? Eric gets on a quick call with Ben and Sam, one of their material suppliers. They review the material datasheet for a new glass fiber-filled ABS plastic, which may do the trick. Back in 3D Experience SOLIDWORKS, Eric adds the new material to the database and reruns the analysis. That made a huge difference. Now the deflection is well below the 1 millimeter threshold. Comparing the stress results between the 2 iterations, Eric easily sees that the additional ribs are doing their job. Feeling confident with the new design, Eric saves to the cloud and increments the revision.
Awesome mechanical analysis. Kinematics, stiffness, and strength. Eric explored detailed results that gave invaluable feedback before any tooling was cut. Not only are all these design revisions captured, but also ancillary discussions about documentation on the new material. Now that the space unit is close to manufacturing, what about the assembly fixtures? We better check in with Dan and see what he's been up to.